Given a partially filled 9 by 9 Sudoku board. Fill every empty cell so each row, each column, and each 3 by 3 box contains digits 1 through 9 exactly once. The board is modified in place, and the puzzle is guaranteed to have one valid solution. In the example, many cells begin as blanks. A solver must choose digits that satisfy all 3 Sudoku rules at the same time. As a few blanks lock into place, the final completed board emerges as the required output. In valid Sudoku, we parsed a static board. But to solve a Sudoku puzzle, we have to fill in all the empty cells yourself. If you write a naive recursion that dynamically scans across rows, columns, and boxes every single time you want to try a digit, your algorithm will execute hundreds of thousands of redundant lookups. On highly restrictive, difficult puzzles, your execution will freeze and time out. We need a way to validate guesses instantly without rescanning the board. Our first massive tactical optimization is to establish instantaneous tracking vaults before we start guessing. We build truth tables representing our rows, columns, and boxes. We do a single pre-scan of the starting puzzle. If a 5 is already sitting in row 0, column 0, we lock it into our trackers. Now, we never have to scan a row or column again. We can verify if a digit is safe to place in a fraction of a nanosecond by simply peeking at our tracker slots. Instead of making our recursive function waste loops constantly hunting across the matrix looking for the next empty period character, we compile a dedicated hit list. We scan the board once and harvest the precise coordinates of every single empty cell, storing them in a flat list. Our recursive engine now has a flawless roadmap. It can advance directly from one empty cell to the next along a straight, predictable timeline. Now we let our depth-first search engine run down the empty cell timeline. At our first slot, we try digits 1 through 9. If a digit passes our quick tracker check, we place it on the board and immediately flag it as active in our vaults. But what happens if our guess causes a catastrophic deadlock 10 steps down the line, leaving a future cell completely unsolvable? This is where backtracking shines. Our recursion cleanly bubbles back up to our original cell. We perform a precise time travel undo, we erase our bad guess, flip its flags back to false in our tracking vaults, and seamlessly try the next candidate digit. Sudoku is guaranteed to have exactly one unique solution. The moment our timeline index reaches the end of our empty cell list, we pull the master escape hatch. We return true up the call stack. This instant signal freezes our tracking arrays and halts all further exploration, preserving our beautifully solved board and returning it instantly. Let's translate this architecture into code. We start by initializing 3 fixed-size tracking tables for our rows, columns, and subboxes. The extra digit slot lets us map digits 1 through 9 directly to their matching indices without confusing zero indexing. We run a quick initial scan of the board. Any starting digit we find immediately toggles its respective trackers to true, instantly creating a real-time security barrier across the entire puzzle. At the exact same time as our initial scan, we isolate our target spaces. Every time our loop encounters an empty cell containing a period, it logs those precise row and column coordinates into a flat list. This becomes our tracking itinerary. By compiling this hit list up front, our recursive backtracking function won't have to waste time searching the board for the next blank space, it can follow a perfectly mapped timeline. Now we kick off our recursive engine, passing in our current hit list index. We extract the row and column coordinates for our target cell, and spin up a loop to test digits 1 through 9. For each digit, we run our instant check. If it is false in our row tracker, false in our column tracker, and false in our box tracker, it is perfectly legal to place. We write the digit onto the board and toggle all 3 of its tracking flags to true. With our digit locked in, we recursively call our backtrack function, passing an index +1 to solve the next empty spot. But if our choices down the line trigger a deadlock where a future cell has 0 valid moves left, the function returns false. Our current frame catches that failure and instantly executes our backtracking cleanup. We erase the bad guess from the board, flip its tracking flags cleanly back to false, and let the loop advance to test the very next digit. We completely reset our tracks before trying an alternate reality. Unlike combinatorial searches where you have to find every possible variation, a valid Sudoku puzzle is guaranteed to have exactly one unique solution. The moment our index equals the size of our empty cells list, we have crossed the finish line. We return true. This acts as a master escape hatch, cascading backward through the recursion stack, freezing our board configuration in place, and halting all further execution. The puzzle is solved. For a Sudoku solver, the worst-case search time is O of 9 to the e, where e is the number of empty cells. Each empty cell may try up to 9 digits, but each tracker lookup is constant time. Space is O of e for the empty cell list and recursion stack, while the row, column, and box trackers are constant size for the standard 9x9 board. First, the setup routine scans the board once. It records every empty coordinate and turns on the row, column, and box flags for every starting digit. Next, the backtracking routine walks the empty cell list by index. It places a legal digit, recurses, and if that path fails, it clears the board cell and all 3 flags before trying the next digit.